So let's say you wanted to know where the center of mass was between this 2 kilogram mass and the 6 kilogram mass. Now, they're separated by 10 centimeters, so it's somewhere in between them, and we know it's going to be closer to the larger mass because the center of mass is always closer to the larger mass, but exactly where is it going to be? We need a formula to figure this out, and the formula for the center of mass looks like this. It says the location of the center of mass, that's what this is. This XCM is just the location of the center of mass. It's the position of the center of mass. Is going to equal, you take all the masses that you're trying to find the center of mass between, you take all those masses times their positions, and you add up all of these m times x's until you've accounted for every single m times x there is in your system, and then you just divide by all of the masses added together. And what you get out of this is the location of the center of mass. So let's use this. Let's use this for this example problem right here, and let's see what we get. We'll have that the center of mass, the position of the center of mass is going to be equal to, all right, so I'll take M1, which you could take either one as M1, but I already colored this one red, so we'll just say the 2 kilogram mass is M1, and we're going to have to multiply by X1, the position of mass 1. And at this point, you might be confused. You might be like, the position? I don't know what the position is. There's no coordinate system up here. Well, you get to pick. So you get to decide where you're measuring these positions from, and wherever you decide to measure them from will also be the point where the center of mass is measured from. In other words, you get to choose where x equals 0. Let's just say, for the sake of argument, the left-hand side over here is x equals 0. Let's say right here is x equals 0 on our number line, and then it goes this way, it's positive this way. So if this is x equals 0, halfway would be x equals 5, and then over here would be x equals 10. We're free to choose that. In fact, it's kind of cool because if this is x equals 0, the position of mass 1 is 0 meters. So it's going to be, this term's just going to go away, which is okay. And we're going to have to add to that M2, which is 6 kilograms, times the position of M2. Again, we can choose whatever point we want, but we have to be consistent. We already chose this as x equals 0 for mass 1. So that still has to be x equals 0 for mass 2. That means this has to be 10 centimeters now. And then those are our only two masses, so we stop there and we just divide by all the masses added together, which is going to be 2 kilograms for M1 plus 6 kilograms for M2. And what we get out of this is 2 times 0 is 0, plus 6 times 10 is 60 kilograms centimeters, divided by 2 plus 6 is going to be 8 kilograms, which gives us 7.5 centimeters. So it's going to be 7.5 centimeters from the point we called x equals 0, which is right here. That's the location of the center of mass. So in other words, if you connected these two spheres by a rod, a light rod, and you put a pivot right here, they would balance at that point right there. And just to show you, you might be like, wait, we can choose any point as x equals 0. Won't we get a different number? You will. So let's say you did this. So instead of picking that as x equals 0, let's say we pick this side as x equals 0. Let's say we say x equals 0 is this 6 kilogram mass's position. What are we going to get then? We'll get that the location of the center of mass for this calculation is going to be, well, we'll have 2 kilograms, but now the location of the 2 kilogram mass is not 0. It's going to be, if this is 0 and we're considering this way as positive, it's going to be negative 10 centimeters because it's 10 centimeters to the left. So this is going to be negative 10 centimeters plus 6 kilograms times, now the location of the 6 kilogram mass is 0 using this convention, and we divide by both of the masses added up. So that's still 2 kilograms plus 6 kilograms. And what are we going to get? We're going to get 2 times negative 10 plus 6 times 0, well, that's just 0. So this is going to be negative 20 kilograms centimeters divided by 8 kilograms gives us negative 2.5 centimeters. So you might be worried. You might be like, what? We got a different answer. The location can't change based on where we're measuring from, and it didn't change. It's still in the exact same position because now this negative 2.5 centimeters is measured relative to this x equals 0. So what's negative 2.5 centimeters from here? It's 2.5 centimeters to the left, which, lo and behold, is exactly at the same point since this was 7.5 and this is negative 2.5 and the whole thing is 10 centimeters. It gives you the exact same location for the center of mass. It has to. It can't change based on whether you're calling this point 0 or this point 0, but you have to be careful and consistent with your choice. Any choice will work, but you have to be consistent with it, and you have to know at the end, where is this answer measured from? Otherwise, you won't be able to interpret what this number means at the end. So recapping, you can use the center of mass formula to find the exact location of the center of mass between a system of objects. You add all the masses times their positions and divide by the total mass. The position can be measured relative to any point you call x equals 0, and the number you get out of that calculation will be the distance from x equals 0 to the center of mass of that system.